I must confess at the very beginning that I know very little about cricket. I used to try and play when I was at school, and I was absolutely hopeless. So I really didn't take much interest in it. My collaborator, Pete Phillipson, is the person who's cricket mad. And in fact, this work started when he did his, what you might call an honours project with me in 2001. And he then went on to do a PhD on something else, and he went to do a couple of postdocs, things like that. And now he's actually become a lecturer. He realises he's got to get more publications. So he's got a newfound interest in this. And so we're about to submit, hopefully, to JRSS-A. So a paper's almost done. So just a little outline. What are we trying to do? What's been done before? What sort of data do we have? A basic model, I call it initial model, and there are key problems with that, and I'll just go through how we've extended that to be more realistic. As a Bayesian, we're going to put prior distributions on things, and we're going to, as usual, simulate realization from the posterior distribution using Markov chain Monte Carlo. And you can just go to sleep for this and just wake up for the results. I've got some nice pictures, well, nice pictures for MCMC anyway, of results. So here's the motivation. It's a quote from Don Bradman. Dealing with comparisons in cricket is harder and more complex than in most other sports. Averages can be a guide, but are not conclusive since pitches and conditions have changed. And that's sort of a key flavour of the modelling that we're going to be doing, is that a lot of ranking tables are based on these averages, and they don't take account of various other aspects which hopefully I'm going to be taking account of in a proper way. Now, you may be aware that analysis of sports data is much more popular, particularly with spread betting companies nowadays. It's very lucrative. People make millions and millions. Indeed, one of my former PhD students actually runs a sports betting company for some millionaire. He doesn't actually own it. So it can be very lucrative. And they're increasingly used. You get all these stats all the time within game stats about, how many people touch their nose with their right hand on the Wednesday and all this sort of bonkers stuff. Some of it's actually relevant. So what's been done in this area? Well, I'm sure there's lots of stuff being done, but the key bits that we've looked at are some work just after the Second World War. And they modelled, these two people separately modelled cricket scores, and they were looking at first-class cricket, and they used a geometric distribution for the actual batting scores on different occasions. And they said they found a reasonable fit. Well, we're going to dispute that. Pollard et al., they looked at county cricket and found that a negative binomial distribution is a good fit. And that's what we'll find as well. And so did these other people, Scarf et al. The negative binomial distribution was a good fit for runs scored. Alan Kimber and Hansford, they looked and considered geometric distribution, and I'll be doing an analysis whereby we can compare to see how good a fit the geometric distribution would be. And they concluded, I've put it in italics here, there was little evidence against this model in the upper tail. I don't know quite how far in the tail they were. But one of the key problems, as I'm sure you appreciate, is the number of ducks, which is not in the upper tail. Okay? So I'm not quite sure what the benefit of using a model is where you can't use it for most of your data. But nevertheless, they got a paper out of it. But one of the things that's particularly good that we're going to make use of is independence of cricket scores for a batsman. No major evidence of autocorrelation, and they used a point process approach. Now, it may be that perhaps that flies against intuition. You might think that people, when they're on form, you've got correlation over the innings and that sort of stuff. But we're going to ignore that as well. It's, I guess we could amend things to have some sort of AR1 type correlation over time or something with a longer reach, but we're not going to do that. What we're going to try and do is to rank all test match batsmen who've ever played. And taking into account all sorts of things, different players have different abilities. Players mature and decline at different rates, so you may be the typical player improves till they get to their peak age and then goes back down again, but individual players can improve rapidly and go down slowly, so we're going to have individual deviations from what you might call a typical aging profile. We're going to take account of stuff that we have in our data, what country they play for, who are they playing, are they playing away or at home, what innings they're playing. We're going to allow possibility of different skill levels over different decades and some sort of residual year effects which are going to be a surrogate for all sorts of changes that might have happened in the rules. So taking all that into account, the nature of the model that we're going to look at is this idea of forming bridges from the past. And the model comes from one by Scott Berry in JASA. In fact, it was 1999 and he got an award for Best Outstanding Applied Paper in JASA, so that's not bad, is it? And basically, we've got all these batsmen who've ever played, and of course the people who are alive now didn't play the people who were alive at the beginning, but the people who are alive now played with people who are still alive but don't play cricket, and they played against people, and they played against people, and so you can get this sort of bridging all the way back. And this is a basic idea. And of course, the information is contaminated because there have been, different rules. Don't ask me what they are, but this is what I'm told. The depth of competition, there are more test match countries nowadays than there were originally. We know who the first two were. They're in the room. Technological advances, game conditions, game focus. These are all sort of euphemisms for things that have changed over time. We've got 1,022 test match batsmen from the first test in 1877 up to the test that we've got, the last test we got in September of this year. Okay, so that's fairly up to date. And there are currently 10 test playing countries. And what I thought was interesting is how much more cricket there is played now. How many more tests there are being played now than was originally. If you look, it took 31 years to get to test 100. Okay? And then 52 years to get an extra 400. But look what's happened here. It took the sum of those to get to test 1,000, and it's only taken 27 years to get to test 2,000. So there's much more test cricket going on now. So we're going to actually exclude some very young or very old batsmen because we don't have enough people of similar ages. We're going to model how people improve with age and then get to their peak and then go back down again. And if we actually have people below 17 or above 42, there are insufficient numbers to actually estimate those things reasonably. So we're just going to chop those out. And as in this historical batting average database, we're going to require batsmen to have played at least 20 innings. So does everyone know about cricket? I know I didn't. Do you need all that? I didn't know about this. Did you know that 29 tests were played at neutral venues? Mm-hmm. Some people were saying they didn't, and I certainly didn't. Really? Oh, it is. English-Pakistan, yes. UAE. Yeah. Yeah. And these are going to be classed as away matches for both sides. Okay, so this is a typical batsman. This is Ian Bell, English batsman. And this is his innings against Australia in these years. And these are consecutive innings. The innings number is the number you can see. And the triangles are away matches. The circles are home matches. The open symbols are there. There's a second innings away, and he was not out. 70-something. Okay? But what's... Perhaps you're not surprised by this. I was quite surprised. It's quite popular to get a very low score, even if you're a good batsman. Right? So if you imagine that you've got to have some sort of statistical model, it's got to try to capture that sort of variation. They can get, centuries up here, and not outs that are quite good, but also a lot of the time, they're abysmal. Obviously a lot better than me, but nevertheless not very good. But in the tens, if that. So we've got to be able to capture this sort of thing. Well, a standard model for count data is the Poisson distribution. You can imagine potentially a Poisson process, a constant hazard of scoring a run, this sort of thing. And so the number of runs scored might have some Poisson distribution. So here I is the player, J is the year, and K is what the innings of that year that they're playing. And so what we're going to do is to use the model that was in this JASA award-winning paper, where you've got a log linear model here. So let's have a look and unpack this a little. So lambda here is the rate at which they're scoring. Okay, and that's going to depend on some player ability score. There's going to be an effect that depends on which year they're playing. This complicated looking thing is a player-specific aging function. So that is what age they were when they played this innings, and the subscript I denotes the fact that each player has their own aging function. Okay? There's the effect of playing at home, if they did play at home. There's the effect of which innings it is, and of course who they're playing. And so what we're going to try and do is to estimate all these things in a coherent way. Well, the year effects, you might think, if you just go back to this sort of model, why do you need these year effects? Well, in fact, these are sort of a composite effect for all sorts of things that have happened. As I mentioned earlier, there are many more test-playing countries than there were initially. The scoring rates are far higher in modern times than initially. There have been law changes. There have been some subtle effects. Now people are trying to make a lot of money out of cricket, and so they're making sure that the pitches are prepared so they can last for 5 days. We've got to take into account the fact that there's no annual fixture list, so it may well be in any particular year you don't get to play the easy side or the hard side and this sort of stuff. And overall, we just want to sort of soak up the changes in the, if you like, the average number of runs scored in a particular year caused by these sort of deviations from the model. We've got data for 139 years, and so we can identify it. I'm just going to set the last year to be 0. So when we look at the fit, it's going to be comparing to see how well people would do if they were playing in 2015. Okay. In what we do, obviously, if you think back to your standard analysis of variance, there are different ways of handling problems of constraints. If you have an overall mean mu and you have a treatment difference, you can't estimate separately the mu and all the treatment means. You can have the treatment means add up to 0. That's a standard thing to do. Or alternatively, just make treatment 1 have an effect of 0. So in other words, the mu is not the overall mean, it's the mean of treatment 1. These sort of corner constraints are a lot easier to handle. So this is an aging function. So A here is the age, going from 17 to 42. And let's have a look at it. What it's saying is that alpha A is what is the average age ability, the effect on the runs scored of someone aged A. So there's an overall mean function without these psi's in, and it's a piecewise constant function. So it starts off, and every year it sort of changes. Okay? We're not restricting the fact that it has to be monotonically increasing and then decreasing or anything like that. So we've got quite a bit of flexibility here. Notice that in this range of years that we think people are going to be at their optimal, there's no sort of player-specific term. But these psi's are, if you like, to allow players to actually learn to play quicker or slower, or to deteriorate slower or quicker than the average player. So these psi's, if you like, are ways of augmenting the aging function, the average aging function, that allows variation between players. So the average value of these psis is going to be 1. Okay? And so we've got this piecewise constant. So we're going to be estimating these psis and these alphas. And again, for identifiability, we're going to think of the peak age as being age 30 in the middle of this interval here. So you might say, well, who on earth thought of this? Why is that relevant? Well, it was a sensible a priori belief of my colleague. He thought that sort of function made sense to him. Obviously, you can dispute it, and in particular, you might say, well, this 27 really should be 26, or this should be 34, or 30, or something like that. But what we looked at is, does it make any difference? We're not estimating these numbers, for example, in our analysis. And it turns out that the analysis isn't very sensitive to these numbers here. So hopefully it's not too important, the fact that this is 28 and not 29 or 27. So that's your typical aging function. As someone gets older, they improve. They're at their peak for a few years, and then they deteriorate. That's typically what happens. And these psis are just ways in which individual players can deviate from the average. So what other things do we have? Well, we've got a home effect and an away effect, so we're going to make the home effect 0 so we can estimate the away effect. We're going to assume the innings effect is 0 for the first innings, and we've got these other things for the other innings. And we're going to fixate on Australia. Okay? It turns out to be first in the alphabetical list, and for no other reason. Okay? So this is the country. So when we look at our analysis, we're going to be looking at somebody who is as if they're playing in 2015 at home in the first innings against Australia. Okay? Now, it's not quite that, because we do have Australian batsmen who won't be playing against Australia. So it's just a way of thinking about it, but it's just because of these corner constraints. Okay, so obviously we'll all be looking out for omega-3. So this is the model. I've gone through these little bits here. So as I was just saying, that if we take if we exponentiate this, e to the theta is going to be the expected number of runs when all of these factors are 0. So the person's playing at their peak age, at home, in the first innings against Australia, taking place now. Okay? So what we're going to be doing is not only estimating these different things, but also looking at the posterior distributions of these exponentials in order to sort of rank batsmen. So what about this Poisson model assumption? It's quite a restricted assumption. The mean equals the variance, and that data on Ian Bell didn't seem to look like that. So how are we going to allow for extra Poisson variability? Well, we're just going to do the standard thing and assume some random effects. So we're going to have all these random effects with mean 1. So we're going to augment. We're going to have a random variable in here that's going to induce a larger variance on x. And there are all sorts of distributions you can use, but the nice one to use, of course, is the gamma one, because when you integrate out the random effect, you get a negative binomial distribution. So this is the reason why we think a negative binomial thing works, and hopefully you'll see that it will fit quite well. In particular, we're going to allow a different random effect distribution for each player. So this is going to depend on I. I is the player. Okay? So the effect of this is on the variability in the runs is that if this was a Poisson, we'd just have this term, lambda ijk. But because we've got the random effects, we get this additional term here. So it allows it to be quadratic, and if it's not that quadratic, then eta I could be large, or if it's very quadratic, eta I can be small. And so you're allowing different levels of variability for different players. And this is the negative binomial that these people used anyway. Okay? So there are all sorts of issues, even though we've got that, there are still further issues that we need to take account in the model. The so-called not out problem. So here we've got Graham Thorpe. There he was, 64 not out. There are lots of different ways you can have not outs. You get about 9% of not outs. And if you include not outs because you've reached your run target or declared, then it can get up to 13%. So it's quite a significant factor in the data. The standard way of dealing with it is well, I guess, what else would you do if you didn't know any better? You know, it's not a stupid thing to do. It's an easy thing to do. You just look at the total number of scores, so you add up those numbers, and then you just divide by the number of completed ones. This wasn't completed, so you don't divide, you don't take that one into account. But that's a very simple thing to work out, but we're more used in statistics to thinking of these things as being censored data. We don't know what score it would have got, but we know that it's going to be larger than that. So we deal with this in a sort of a very standard censoring mechanism. Also, ducks cause lots of zeros additional to this negative binomial model. There are about 10% of the observations are ducks. That's having excluded those that were zero not out. Okay, and here's another score that, again, I didn't know about. Don Bradman, not bad. His most popular score was 0. Okay, now most people wouldn't think that, but it's because of this, you know, this capricious nature, as my colleague keeps calling it. If you look at it, you know, even though you're doing really well when you're not 0, you do get zeros, and so that's life. So what are you going to do about it? Well, we're going to have a zero inflated solution. So the probability of getting a 0 is going to be a mixture between a point mass at 0 and this negative binomial distribution. Okay? And we're going to allow that to be player specific because different people have different propensities to get ducks. Okay? So it might be, for example, well, there is a probability of 0 in the negative binomial, but there's a boost on that for each player. And we'll see the effect as to how different this is for different players as well. So, what about the prior distribution? Well, there's quite a bit to tell you here. I suppose we've got a few hours, haven't we? The player skill level, we're going to try to batch players into decades when they're born. You might argue, well, perhaps it should be when they play rather than when they're born, but, you know, 6 and 2/3, I suppose. So what we're going to say is that the playability of player I, that's theta I, is going to depend on what decade they were born in. It's just you know, it's allowing for different eras in time, I guess. And we're going to say that this is a continuous quantity. It's going to have a normal distribution, and we can specify the mean and the variance of these different decades. And we've got some priors on these things, so we've got sort of a hierarchical prior here. So that's for all 1,022 batsmen. Now these year effects, remember, we're going to compare according to if they were playing today in 2015, and so this delta for the 139th year is going to be 0. But what we're not wanting is to have independent year results. What you end up with is very noisy information. So we're going to think that these year results are fairly smooth over time. And we're going to implement that smoothness by having a backwards random walk. So, for example, in year 138, that's going to be 0 plus some normal noise. And in year 137, it's going to be that in year 138 plus some normal noise. It's just a way of smoothing these estimates. Because you wouldn't imagine, well, I didn't imagine, that these year effects would be all over the place. You know, the year effect for 2 consecutive years aren't going to be incredibly different. And how might we express that? Well, we put some smoothness in the prior. And so the way we can fit this is that you can think of it in this way, it's a nice way of thinking of it, but the multivariate distribution of all these 138 deltas is a normal distribution with mean 0, and it's got this precision matrix here. It's got this banded precision matrix, and that just makes, you know, you can think of this as an object with all the deltas in rather than the individual deltas. It helps when you're doing the MCMC. So, what about the age effects? Well, again, we're going to think that someone actually improves, they get to their peak, and then they decline. So this is a typical player now. And remember that an actual player is going to have these things augmented by their side parameters. So these, you might think, well, where on earth did these numbers come from? Well, they came from thinking that 7 years before they hit their peak period, they're going to be 2/3 as good as when they get to their peak. Well, why 2/3? 3/4. What a fraction would you like? We've used 2/3. And after 32, 7 years later, they're going to be about 2/3 of their peak performance. Okay? So this is our prior belief, and of course everyone's entitled to their own prior belief. The results weren't very sensitive to this choice anyway. You've got to put something in. But we thought that these things would be much more smooth than the year effects. If somebody is playing much better than everybody else one year, then they're going to be playing much better than everyone else the next year and the next year. So there's much more correlation over time. So instead of using a first order random walk, we've used a second order. So here we are. The residuals from our prior mean function are going to have this second order random walk. And that makes life wonderful, of course. So there's a lot on this slide. If we just fixate on alpha 1 is the age effects for those before the peak age of 30, and alpha 2 is for the age effects after 30. And it turns out that with this model, if you think about it, because you've got this second order correlation, you know what the value is at 30, and so what's going on in this half is independent of what's going on in this half. Okay, because they're just conditionally independent of one another, because you know that at age 30 the effect is 0. And so again, you've got these sort of high-dimensional multivariate normals with particular precision matrices. But these are just useful in the fitting. You don't have to fit all these different alphas independently of one another, because otherwise your MCMC will fall over. On these other parameters, I've put that we've got a weak prior. So what do I mean by that? Well, remember, all of these parameters work on the exponential scale. It's a log linear model. So e to the 2 times a half is 2.7. Why am I telling you that? Well, what we've done is choose, so the 0.5 here features here as a standard deviation quite a bit. What it means is that we don't know what an individual player's maturing or declining parameter is, but we really think that they're going to be within 2.7 times the average, or 1 over 2.7 times the average. That's quite a range, actually. So we don't think the means are going to be 1, but we're going to have standard deviations of 0.5. The same for this thing, the effect of playing away from home. So this is quite a large change, a up factor or a down factor of 2.7, quite a big change for the innings effect. The random effects, remember, these have to be log normal in order when we marginalize it, then we're going to get a negative binomial. And so this has got median 1, but it's got a largest variance. That doesn't look like a large number, but in fact on this scale it is quite large. And in terms of zero inflation, how many extra ducks are we expecting to see? We're going to model this with a beta distribution with parameters 1 and 9, because we think that it's going to be about a 10% inflation of ducks. Remember, we thought it was probably around 30% in the data, but we don't want to look at the data and then decide our prior. Goodness me, we'd be shot if we did that. But we don't think it's going to be much bigger than 30%. Okay? So again, you've got to specify something. It's mildly informative, but not very informative. So I call this sort of weak prior information. So what are we going to do? Well, we've specified a model for the outcomes of runs, and we've specified a prior distribution. So all we're going to do now is to build some MCMC algorithm to simulate from that. Now, these thetas were normal with a conjugate prior, so these are just nice Gibbs steps. A lot of these other parameters, we're going to use Metropolis-Hastings steps with symmetric normal random walks on whatever scale is appropriate. So, for example, these etas are positive, so we're going to have normal random walks on the log scale. these probabilities on 0, 1, so we're going to have it on the logic scale, just sort of standard things just to make the thing work. Unfortunately, these parameters, the year effects and the age effects, because we've induced this either first order random walk or a second order random walk, that's put a lot of dependence between neighbouring effects. I mean, after all, that's why we did it. So it shouldn't be surprising that that's what's happening in the posterior distribution. So the posterior distribution for the effect of year L depends an awful lot on the ones on either side of it, because we put in this smoothness, so it's bound to do that. So if you just try and do sort of simple random walks on this, proposals, you think it'll work. So what do? Well, you look and see what somebody else did. So Danny Gammerman suggested a little while ago that what you should do is you should look at the function which is minus the log of this full conditional density and look at a second order Taylor expansion. Okay? And then you get this. And of course you look at the second, for the log, second order, normal. That's what it's all about, getting a normal proposal. Okay? So you can sort of see what's going on. This is quite a large dimensional distribution, unless you're someone who does spatial analysis, and then you'll think this is pathetically small, but for me that's quite a high number of dimensions. What you've got here is you've got the curvature of the log function, and here you've got something that's trying to find the mode. And in fact, Ruan and Held suggested instead of just using delta tilde as your current value in your MCMC, but you just iterated on this, and then that means that you get an independent proposal which matches the mode. So your normal, the mean of your normal distribution matches the mode of the thing that you're trying to aim for. And that's when we have a first order smoother. When you've got a second order smoother, it's just as bad. So you've got to do these sort of rather complicated, but not that complicated, but quite effective proposals in order to get a rapidly mixing chain over these high dimensional parameters. Unfortunately, because you've got these sort of rather complicated parameters, you can't just say, oh, well, I'll just use RJAGs. I'll use WinBugs. If we didn't have this smoothing, you could actually just write all this in WinBugs and then it'd save a lot of time and effort because someone's developed the software for it. But as far as I could see, I couldn't see how we could actually get it to use these sort of proposals. So what does that mean? That means you've got to write your own code, or indeed have somebody to write it for you. Much better. So, over the centuries he got that to work, and get a little bit of burn-in for the MCMC, and then just run it for a lot longer, thinned it a bit, so that we got almost an autocorrelated realizations, about 10,000. So we're going to have about 10,000 as if they're like a random sample from the posterior distribution, and that's what we're going to use to look at our results. Don't click twice. So this is the decade mean. Mu d was the decade mean on the log scale, so I've exponentiated it. So it's a bit like a posterior decade mean runs. And so here we've got before 1859 and right the way back to more present after 1980. Now, it's not clear to me why my dear colleague hasn't done it up to 2010 or something like that, something nearer. So that's after 1980. There should be more of these. Ah, that's what it is. I'm glad somebody's thinking. That's what it is, yes. Particularly if we're not allowing youngsters to play. So let's have a look. What have we got here? Obviously, there's variation in here, and of course, we could have made life even worse for ourselves by smoothing these as well. This is what happens when you assume independence between decades. Now, imagine if we'd assumed independence between years, how much moving up and down there was, because that's what we did originally. We thought, goodness me, that's nonsense. But nevertheless, it's all much of a muchness. So high values means that lots of runs were scored. Low values means... So, for example, for people born in the 70s, it was relatively hard to score runs compared to people born in the 80s or the 60s. Does that make any sense to you? That's what the data are telling me. What about variability? There seems to be quite a bit of variability. It looks to be less variability here in the 50s for people born in the 50s. But overall, you know, they're all fairly similar. We could have smoothed these a bit. That would just pull this one up. But so what we're trying to do here is to trying to take account of what's going on in different eras. So we're just looking at decade effects. Very, very, very broad brush. So what about these year effects? Remember, the effect at 2015 is 0. And so what we've now got is we've got this sort of backwards normal random walk. So that's smoothed it. Imagine what it would have been like if we hadn't have smoothed it. Okay. Now, of course, this is plotted on the exponential scale. So this is a multiplicative effect of year. So no effect of year is this horizontal line at 1. And for very few years does the confidence band not include 1. So it's almost as if, you know, well, although, you know, it's not exactly 1 in every single year, there's a lot of uncertainty around that. So I have no idea what happened here. So that's what, 1980 something, 1990. Hmm?
A lot of wet pitches.
Ah.
And a very weak team because of the
There you see. I'm glad this has been recorded so I don't have to write this down.
So this is the effect of an individual player or the Australian team?
This is the effect on every player of playing in a particular year, having taken account of the effect of being born in a particular decade. Okay, but essentially, it's all 1. There's not a lot of effect there. What about this aging function? Well, there we've got the. Now remember, this isn't exactly drawn correctly because this is a piecewise constant function, so this should be a step function. Okay, but nevertheless. You just join the dots, as it were. So we know that at age 30, the value is 0. Exponentiate it, we get the value 1. Okay, so that's the fixed point. And so what we've had is we've had a second order random walk smoother this side and another one going that way. Okay, and as you might imagine, there are fewer players playing over 40 and there are fewer players playing under 20. We don't allow them to be playing under 17. And so the uncertainty there is larger. The thing I don't understand is this. Right? So what we expect it to go up and then come down. But it starts coming down and then goes up again. So what we're wondering is whether or not for someone to be playing test match cricket age 35 onwards, they've got to be very good. So what it is that the people who are contributing here are no longer selected, right? And that's why. And so, in fact, and of course, this feeds through into the individual profiles because all we're doing with the individual profiles is scaling them by these size. We're going to scale this slope here, and we're going to scale this slope here. So we'll still see this bulge. So it's not a random person who plays age 30, 36. It's those players who really do play at age 36. What, picking a team, selection bias? So this is an interesting plot. So what we're seeing here, again, these are multiplicative factors because they're additive on the exponential scale. And what we've got here are the effects of playing these individual teams. Okay, so here we are. There's our uncertainty about what it's like to play Bangladesh. So it looks like, relative to playing Australia, where that's a factor of 1, you typically get about 70% more runs against Bangladesh. Okay? Zimbabwe, I don't know, about 35% more, something like that. So there we are. There's England, and it's consistent that it could be 1. But it's a bit, the median's about it, that's what we're dealing with, uncertainty here. Okay, South Africa is nearer to 1. Okay, so you can see the effect, and these actually might fulfill all your, what you might call your beliefs, or some people might call your prejudices. Right? So you might expect these to be the ones that are near 1 to be the ones that you'd expect to be near 1, and the ones that are floating off to be, you know that they're not very good. Look at the effect of innings. The effect of innings 1 is 1. So, not surprisingly, innings 2, it's harder to get runs. Innings 3, it's hard to get runs. Innings 4, it's hard to get runs. And it's harder to get runs when you're playing away. I mean, if that had been up there, then there's been something wrong, wouldn't they? We all know that's the way the sport typically works. But one thing that is quite nice about this plot is that because it's a multiplicative plot, what you can see is that the effect of playing England in the second innings, because if you multiply those two things together, you'll get almost 1. It'll be a bit like playing Australia in the first innings, because that's the way these things interact with one another. So you've got these trade-offs. So playing Pakistan away in the first innings is about the same as playing Australia at home in the first innings. That's of course, that's putting an awful lot on the model, of course. But that is the model. What about these random effect parameters? Remember, every player had their own random effect parameter, and the geometric model assumed that this parameter was 1, and the Poisson model assumed it was infinite. Well, here we've got the 5-number summary of their mean. So typically, players were getting values of about 0.88. About 25% of them had values bigger than 1, but obviously 75% of them didn't. So it looks to me that we were quite right to allow different values. We could have had a common value for everyone, but it looks to me that there's sufficient player-to-player variability here that we should allow different values of this parameter. And the same is true of the zero inflation parameter. Again, if 0 would be the case if we just had a negative binomial distribution, but we've got this zero inflated negative binomial, and typically that's about 6%, but it can go quite high, 30-odd%, or quite low. So it seems to me that there's sufficient variation in these numbers that it needs to depend on player, and all of these are a lot of these are sufficiently different from 0 that you wouldn't be doing the right thing to not have the zero inflation in the model. So this is a bit where we start getting personal. So you're going to get a clue as to who's going to be the best batsman. I didn't think it was worthwhile putting his profile on, but we just the fag end of it was all right. So you can see, basically, this is what happens. They go up, they sort of level off a bit, and then they go down. And these are augmented by those player-specific maturing and declining rates. But they all have this, because they're essentially multiplying the average curve, which has this sort of bulge here, they've all got this sort of bulge. So here's just a non-random selection of players. It's interesting to see how some of them are quite quick to mature, or they start off higher actually, and some of them are quite quick. They go off quicker. So here's the posterior distribution for e to the theta. So that is the player ability level. So what we think of is that we're no longer interested in just looking at the data and just calculating averages from it. What we're thinking of is every time a batsman goes out to bat, it's an instance of all the times they could have gone out to bat. So there's a distribution on these things. And this is the mean of that distribution. This is for when playing Australia at home in 2015, etc., etc. So there he is, good old Don, playing Australia at home. But he's not doing badly, is he? Yeah. So we knew that before we turned this handle, if he didn't come out top, then we knew we got it wrong. So, yeah, it's a sanity check, isn't it, really? And you may recognise I do actually recognise some of these names. Some of them I've actually looked up on Wikipedia and then instantly forgotten. Nice to see that Joe Root there, another brilliant Yorkshireman. Okay. In the other list I've gone down to 25. Trying to think, well, where is he? That was because Boycott was 25th. Where is he? He's not there, is he? Now, that's another, I can thank my colleague for that, yeah. So, I don't know who E. Jones is, but he must be a hell of a bowler. Right? Not that good on the old bat. But one of the things you can do when you're doing Markov chain Monte Carlo is instead of looking at distributions of scores, you can look at distributions of ranks, because at every iteration you've got a realization of theta, and you can rank according to that, and so you can get distributions of ranks. So the dots here are the median rank, the median in the posterior distribution, and these are the 95%, the central 95% equitail confidence intervals. So it's pretty sure that Bradman was the best. But what's interesting, or potentially interesting, is how wide these intervals are, right? And you can see why they're that wide. There we've got these distributions, and this is saying what we think. This describes our uncertainty about how well they're batting for a typical time that they go into bat. Well, if they could score anything with this distribution, and that person could score anything with that distribution, then what order should you put them in? That's the problem. If you actually just take an arithmetic average or something like that, then you just get a number. And it's, there's no uncertainty on that. But in fact, what the model shows is because we've got this sort of negative binomial with lots of variation, you've got zero inflation, all these sort of things going on, that there's lots of uncertainty about how good they were. And consequently, there's a hell of a lot of uncertainty about where we should rank them. Obviously, there's a typical rank, and we could have a table according to how good their rank was, or how good their mean of this quantity was. You can do all these things. Again, we've got our friend E. Jones, almost certainly ranked at the very bottom, but he could have been ranked a little bit better. You can't say he was definitely the worst player that's ever played Test cricket. You can't actually say that. That would be grossly unfair. And look at this one, R.G. Archer. So that person could be anywhere from in the top 100 to about 750th. There's so much uncertainty. So there we are. Have you written those down? So there's a summary. Let's just have a look. So here we've got the rank. There we are. There's old Jeffrey, number 25. There's Don at the top. This is the posterior mean number of runs and its variability. These are the maturing and declining means. This is their particular zero inflation parameter. Basically, it seems that he needs to have quite a high zero inflation parameter, because when he did score, he scored a lot. That makes sense, doesn't it? And his confidence interval is 1 to 5. Well, look at the next one, Pollock, 1 to 135. Okay, but I still found that intriguing, that he could even be thought to be 1, because look at that difference there. It's because of this variation. Taking that into account. So I thought it'd be easy to see it a bit larger. So there we are. So in fact, the median rank, these are marginal distributions of the rank. So there is no number 2. There is no number 3. So what we're not doing is saying, of these 15 here, what was the most popular ranking of these 15? Okay, because then there would be a 1, there would be a 2, there would be a 3, there would be a 4. Okay. So these are the marginal distributions, so you get these things missed out, and occasionally they go in a different order. But that's just due to the fact that this is a numerical summary of something that's varying. So there he is, Joe Root, number 12. There's Brian Lara. There's Sir Len. Jeffrey. So do these orderings make any... I mean, obviously, this ordering flies in the face of my main thesis, which is that you shouldn't rank by a single number, right? There's uncertainty. There's so much uncertainty in these things, it makes no sense. You should take into account some expression of uncertainty. So all I've done here is I've ranked by the posterior mean run, and that's almost just as daft as ranking by the average that they scored or something like that. These things won't be too far apart. But these numbers take into account who they played, what innings they played, and all this sort of stuff. So, I'm about to finish. I've got the red light there telling me to shut up. Obviously, there are lots of different rankings that are available. There's this one, the highest career batting average, and the ICC ranking. And would you believe they don't give the same ranking that I do? Well, what a surprise. Neither of them allows for uncertainty. Out of the top 25 batsmen, this highest career batting average, I've got 19 in common with theirs, and 15 in common with the ICC best ever ratings. But I like to think that I'm taking into account a lot more understanding of the variability, and even my top 15 isn't the sensible thing either, because you should be looking at these confidence intervals of ranks. There are 4 in my top 25 that aren't in either of these lists, and that's the position they are. So why is that? It's because they are doing an analysis assuming no uncertainty. So this, as I say here, the mismatches here between these lists illustrate a central problem in ranking. If you just use a single number summary, then if somebody else uses a different single number summary, then you're going to get people flipping in and out and flipping in and out. That's not to say that you'll not get that if you take variation into account, but at least there'll be less of that going on. As soon as you say this player was not number 2, he was somewhere between number 1 and number 135, right, then most people would agree with that. They might not agree that it had been number 2. Because it's just, obviously, this is a model, of course, and the model's wrong. But nevertheless, it might be synthesizing some of the important aspects. So it makes sense to have a distribution rather than a single number or an interval that expresses uncertainty. We've been able to take into account lots of player-independent factors, which the averages don't do. They say, well, on average, it all works out. Well, there we are. What's the sample size needed for that to happen? How many innings do they actually play in their lives? They don't play that many. Particularly if they're not very good and they don't get picked on. Anyway, so it seems to me that having a distribution or an interval that takes into account the uncertainty that there is, because of the huge variation there is whether they go in and get a 0 or a 100, that can, happen equally well, then the analyses are going to be much more robust. You're not going to, because somebody got a bad LBW decision means that they're no longer going to be very high up, but that will be taken into account. Because of it would be that sort of bad luck will be taken into account within the uncertainty. Obviously, there are lots of things we could do, but we're getting a bit tired working on this. One of the things, of course, we've got zero inflation. A duck is a big thing, but there are lots of ways of scoring runs. Getting a 4 or getting a 6. Is it a bit easier to get a 4 than 4 ones? It might be, and so it may be that you have to inflate according to the numbers of straight 4s or straight 6s as well as you've got an inflation of 0s. It may be that nuance might work. Obviously, we consider other aging functions. I mean, I think ours is so flexible that, you could actually specify a particular functional form, and then you'd be wrong. But ours is a piecewise constant one, so it's almost as flexible as you can get. One thing that we haven't taken into account is batting position, and I'm sure that will have a big effect on what's going on. We didn't yet have the data for that. We haven't done any formal model comparisons, but it seemed to me that from the E to I summary posteriors and the pi i's, they're also variable. You should vary them according to player, and you should incorporate those factors into the model, because they're not the default values. Of course, once you've actually got a model